Good afternoon. That's more like it. Excellent. First attempt. So today we're going to speak, this is the last week of lectures, and everything that comes this week will be on the final, or can be on the final, and all the lectures can be on the final, okay? So the week after that, we have on Monday, we have a review session about the fourth part of the lectures. And then on Wednesday, we have a review session about everything, okay? And on Friday, I will give you a lecture about Berkeley and the actinides. You do not have to come, but it would be great if you would be here and would hear about Berkeley and the actinides. We are very famous for this, for many other things also. All right, is Henry Doe here now? Where is he? I have his notebook. If you see him, tell him that I have his notebook. It's down here. Today, we're going to talk about redox reactions, redox reaction. As the name says, there's a reduction and an oxidation. Redox. That's not redox, it's redox reaction, okay? So there is no reduction without an oxidation, and there is no oxidation without a reduction. So they belong together. It's called reduction-oxidation reaction or redox reaction. And so Leo goes grrr. Leo goes grrr. No, your professor has not lost his marbles totally today. That's a mnemonic. And the mnemonic Leo goes grrr. You ever heard that before? That's what it means here. Loss of electrons is oxidation. Leo. Loss of electrons is oxidation. Goes grrr. Gain of electrons is reduction. Leo goes grrr. Gain of electron is reduction. And for those of you who may not be so much in favor of animals or pets or Leos, I give you something else. Oil. Rig. Oil rig. Oxidation is loss of electrons, oil, and reduction is gain of electrons. Rig, oil rig. Okay, you need to remember one of those, or both of them, Leo goes grrr or oil rig, because this will help you with your redox reactions. And the point is, redox reactions always involve the transfer of electrons. The electrons transfer from one system, so they go off of one system. That means that system loses electrons. If something loses electrons, its oxidation number, oxidation state goes up. And if something accepts electrons, its oxidation state or oxidation number goes down, becomes smaller. Okay? So that's why I said there is no oxidation without a reduction and no reduction without an oxidation. Leo goes grrr and oil rig. Of electrons, there it came, sort of traipsing along at the end here. So now let's assume a Gedankenexperiment. That's actually an English word, Gedankenexperiment. It's an experiment that we do in our head. Okay? Gedanken are thoughts, a thought experiment. Let's assume you have a piece of copper, and you put this copper metal. Oxidation state of copper, what's the oxidation state of copper metal? 0, okay? Metals are always, in their natural form, are 0, okay? And you put it in a solution of copper sulfate. Cu2 plus, SO4 2 minus. Cu2 plus, what's the oxidation state of copper? 2 plus, exactly. All right, that's that simple. And now we take that same beaker and throw in 1 mole of zinc sulfate. Zn, 2 plus, SO4, 2 minus. What's the oxidation state of that zinc? 2 plus. And we also stick in a piece of zinc metal. So now we have zinc metal in zinc sulfate solution and copper metal in copper sulfate solution. It's a mixture of them. Now, there are several things can happen. Quite a few can actually happen. So the copper could come out, could go in solution, so that copper rod will dissolve slowly. Okay? When it dissolves, it goes into copper 2 plus 2 electrons. Okay? That would be one possibility. So the copper gets oxidized to copper 2 plus 2 electrons. Okay? That would be one possibility. The other possibility is that the copper 2 plus in solution picks up 2 electrons and becomes copper metal. That's the other possibility. We played out. There's the possibility of dissolving the copper. The other possibility is that we played out copper and we reduce it from +2 to 0 and it gets metal. The same is true for zinc. The zinc could go in solution. The zinc metal picks up 2 electrons. Zinc metal goes in solution to zinc 2 plus and releases 2 electrons. Okay? What would that be? That would be an oxidation. Okay? What is oxidation? Leo, loss of electrons. The zinc would lose 2 electrons and they go into the solution and it goes at zinc 2 plus in solution. The other possibility would be that I have that zinc in solution, zinc 2 plus, and it picks up 2 electrons and plates out on the zinc stick there as zinc metal. So that would be the zinc 2 plus 2 electrons. That would be what? It would be a reduction. Okay? So I have 4 possibilities, but that's not possible. We got to make a decision. Either one of them goes in solution and the other one plates out. Which one it is, this is part of our lecture today. So we have copper 2 plus and zinc solid zinc, or zinc 2 plus and copper, solid copper. So we could, actually, this is what happens. So the copper 2 plus goes from solution and it will plate out on the copper rod. It will make the copper rod thicker and thicker. Excuse me, please. At the interruption. So the copper goes from solution into solid copper. So it has to pick up 2 electrons. Copper 2 plus 2 electrons gives copper metal. Okay? So this would be, what would that be? Would be a reduction, isn't that right? Okay. Now where do these 2 electrons come from? Thank you, from the zinc. Because the zinc is a solid electrode, and it says, I want to go into solution, and so I go into solution and form zinc 2 plus and produce 2 electrodes. And these 2 electrodes that are produced, so the zinc gets what? Gets reduced or oxidized? Zinc? Oxidized. Good. You guys are good. Zinc gets oxidized plus 2 electrons, and these 2 electrons are furnished to the copper, and the copper with this becomes then copper metal. So there are electrons flowing, and we have a reaction. We know that this K is larger than 1. That means it's on the product side. K is larger than 1, product side defined. And with this, delta G is smaller than 0. So this is what will happen spontaneously. The opposite will not happen spontaneously. So the zinc goes in solution and the copper plates out. All right? So we call the copper is an oxidizer. An oxidizer. So the copper, the oxidizer itself gets reduced. So this is an oxidizer. Copper 2 plus is an oxidizer. And now it picks up these 2 electrons and gets reduced. Okay? Now it's a reducer, the copper metal itself. And what is zinc then? Zinc metal must be a reducer, and it gets oxidized. All right? So this is the transfer of the electrons. One gets oxidized, so the oxidizer gets reduced, and the reducer gets oxidized. Oh, this is so confusing, isn't it? Yeah. Not really, okay? That's why we are doing this here. So, but at the beginning it will be confusing. And at the end, I hope you will understand. Most of it at least. So that's what I said here. The zinc, in order to get to here, must produce zinc 2 plus 2 electrons. That's our oxidation reaction. And the reduction reaction is these 2 electrons are picked up by this baby here, by the copper 2 plus, okay? And it forms copper metal, and this is our reduction reaction. So this is a red-ox reaction. And so now I have these 2 electrons. They go from here to here and to form this. So now with this we have our equation explained. But you know, delta G, if delta G is negative of a system, the system can do work. But we don't let the system do any work because we let these electrons zip around in the solution going back and forth, or mostly back for one and the other forth. And we don't do anything. How about we make these electrons work? We separate these 2 systems. In the one, we have zinc metal and zinc sulfate solution. And in the other one, we have copper metal and copper sulfate solution. So nothing will happen, essentially, if I have this in its 1 molar solution. The zinc metal sticks in the zinc sulfate solution, and the copper metal sticks in the copper sulfate solution. So that's what we do here. We have zinc metal in a 1 molar zinc sulfate solution. That's the zinc metal here. And we have copper metal, that's the copper metal, in a 1 molar copper sulfate solution. So now I know that the zinc wants to go in solution. Okay? The zinc wants to go in solution. It wants to be oxidized. It's much happier if it's oxidized than it's in the reduced form. The zinc goes in solution. Okay? Let's have the zinc go in solution. That zinc metal will dissolve and will form zinc 2 plus ions. What are they? Cations. Okay? So what is left over? What do we have left on the surface of the metal? 2 electrons. These 2 electrons, they are now on the surface of the metal, and now put a wire here between these 2. And now the electrons can flow over here through that wire, and now this electrode will be negative, have negative charges on there. And so there's these 2 electrons on the surface now. They transferred from here to here. Now there are 2 electrons. The copper 2 plus says, there are my 2 electrodes. My two electrons. And it says, okay, I want these 2 electrons, and I'm going to plate myself out as copper metal. So this comes out of solution and goes onto the copper, so the copper gets thicker and thicker and thicker, essentially. Okay? So now these electrons are doing work. They're flowing through here. We have a difference in potential. All right? So I could put a voltmeter in there and measure that difference here. Or I put a light bulb in there, a small light bulb, or an iPod, or a cell phone, or any electrical device that it will do with 1.1 volt, which you will see, this is 1.1 volt. And this is essentially the principle of a battery, of any battery to use. Of course, they have other compounds in there, and they are much more sophisticated. But essentially, you have an oxidation reaction and a reduction reaction. And the electrons flow from the oxidation to the reduction, and with this, you can use these electrons to drive something that uses electrical energy. Okay? So this is essentially what is a standard galvanic cell. We say standard because this is at 1 molar and this is at 1 molar. See, one of the few times where we have standard state and it does something and we don't have to change anything. This is standard state and this. We have 1 atmosphere pressure, 1 molar solution here, 1 molar solution here. Okay? This is a standard galvanic cell. There was this Italian Galvani. He is the one who invented that and he discovered that. Or no, he invented it essentially. So, but there is something seriously wrong with that picture. So we have put zinc. This thing here will go in solution till there is no more zinc electrode. Then your battery is done, okay? So the zinc is dissolved, all the zinc is dissolved, and your battery is done because your electrode is dissolved. That's when you have to buy a new battery, okay? So, but when it starts dissolving, we have zinc, 1 molar zinc 2 plus, and 1 molar SO4 2 minus. So when it starts dissolving, would we get more positive charges or more negative charges? More positive charges. So we have an electrical imbalance because the number of sulfate ions is not changing. The SO4 2 minus is not changing, but the number of zinc is increasing, so you become more and more and more positive. And so this doesn't work very well. You can't have an electrical imbalance. Nothing will work. So what happens here? So these electrons flow over here, and so copper comes out of solution. This is 1 molar copper sulfate. So at the beginning, copper is 1 mole, copper 2 plus is 1 mole, and sulfate is 1 mole. So it flows out of it goes out of the solution and plates here as copper, takes these 2 electrons and plates here as copper. So that electrode will be bigger and bigger and bigger because you're plating out the copper. So what do you think the charge will be here? There will be an imbalance, will be more negative or more positive? More negative because the sulfate ions haven't changed. So this is why you need a salt bridge. And a salt bridge is a piece of metal, a piece of glass, a tube, and there are many different kind of salt bridges, where you have an electrolyte. We have potassium or sodium nitrate. This is K plus NO3 minus, strong electrolyte, totally dissociated, or you have sodium nitrate, Na plus NO3 minus, and you put this in agar. This is a natural polymer which you could cook up, and when it's at room temperature, it solidifies. And you put the solution in there, and with this you make a solid, you fill it in that salt bridge, and it dries, and then it has this potassium and these nitrate ions in there. And so what will happen, since this here is getting more and more positive, so the nitrate will flow in here, the NO3 will flow in here to make this electroneutral again, that you have charge balance. And this one here, this will have too many negatives, so the potassium will flow in here, okay, or the sodium will flow in here. So with this you have it charge neutral. So we have our oxidation reaction here and our reduction reaction here, and we have our salt bridge. Without a salt bridge, nothing happens. So these 2 electrons, they're flowing along here and forming this reaction then, and then zinc goes in solution, copper comes out of a solution onto the electrode. So this is how you write such a thing. So you have the left side, you have zinc, and this is the zinc electrode. Then you have a bar, that's the zinc solution, zinc 2 plus, and this is 1 molar, you write the concentration here. Then you have this double bars, thank you. Today you helped me, thank you. You have the double bars, and then you write that side here, that's the copper solution, 2 plus, 1 molar, and you have the 1 bar, and this is the copper electrode. That's right, that's how you write this galvanic cell. And if this is 1 molar, then it's a standard galvanic cell. You could have also different concentration here. And so if you measure the potential of exactly such a cell and you do a high precision measurement, you will measure a difference in potential of 1.1 volts. 1.1 volts. Let's do that. So let me explain this to you first. So we have here a solution of copper. That's the right electrode. Copper, see the copper metal? Can you see it? Okay. I stick it in the copper sulfate solution, and the copper sulfate solution is 1 molar. It's nice and blue. Copper sulfate, copper 2 plus is blue. And this is zinc metal here, which I stick in a 1 molar zinc sulfate solution, and this is a clear solution. Zinc doesn't have any absorption in the visible. And I have here, I have a voltmeter, okay? And now let Karen connect that. So what do you read there? 1 second. What do you read? Nada. What's missing? The salt bridge is missing. So I have an electrical imbalance. The salt bridge is missing. So now let's show the salt bridge before we put it in. Show it down here a little bit. Okay, see that? Oh, yeah, very nice. Good camera work. Excellent camera work. So now we put that salt, it's a solid, we put that in, and now look at the meter. 1.07 volt. This is a run-of-the-mill experiment. That's not a high-precision experiment. We just took 1 molar and 1 molar. We didn't polish the electrodes or anything. If you do this, you get 1.1 volt, and we got 1.07, 1.08. That's superb. That's just about, how many percent? 2%, less than 2% difference, okay? That's superb. So 1.08 volt we get with this here. Now, you could do one thing. You could take that salt bridge out, and then I'm using my fingers as a salt bridge. You think that's going to work? Why? Because I'm just a bag of salt? Is that what it is? Let me put my fingers in here. What does it read? 1.06. Okay. Alrighty, so it works. We are nothing but a bag of salt, 70% water, and the rest is actually salt in our fingers, and a little bit of DNA and other stuff, and proteins and enzymes and so on, but this is not the majority. So it's enough to transfer these electrodes from here to here, okay? Now let's do an experiment. The three of you, and I would like you, please. Okay, if you go over there to this side, please. Here, take some glasses. Take some glasses. You need to have safety glasses. So what we're going to do is, no, you stay here, please. If you go move over there, you stand over there next to your colleague there. Here's your glasses. So you come close to here, come closer, so that you can reach in here, okay? And you come close here. So what we're going to do, they're going to be our salt bridge now, okay? And I never did this experiment before. Actually, I did it this morning. But before, I never have done this. And so what we do, you're going to stand here. Turn this way. Okay, this way. Okay. All right. So now I'm going to spray your hands a little bit with water. Okay. Now you hold hands here. And now you reach over. Let me put a little water on there. Hold tightly the hands. Okay. No, you're not. You're not. You hold his hand. Okay. All right, hold tightly. And now you take your index finger. You take your index finger, and you take your index finger. And can we go closer, please? So now put the index finger, 1 second. Put the index finger in there, please. And then wait. We want to see the meter. I need the meter too. The meter. Okay, put the index finger in there. There's nothing happening to you. How about that, huh? 1.05 volts, all right? It works, even this works. So the electrons were flowing there. Some napkins, and can you wash your hands? The electrons were flowing all the way through everyone here, and I would like to do this with the whole class. That would be the first time done in Berkeley. I would like to break a record and have the whole class do this on Wednesday in a week, okay? We do this, and this is voluntarily, but we spend about 50 minutes, and then we have a picture taken of all of us with the Cal sign and a big voltmeter in the front. Are you with me? Yeah, let's do this Wednesday in a week, the whole class, okay? Let's see if it works, because they say it should work if there are hundreds of people. So if I get over 200 people and it works, it would be incredible. So we have it done on video, and we take some pictures of it, okay? All right, go Bears. Wednesday in a week, when R&R is, okay? During class, I have regular class hours next week, just like regular class, yeah? I will do it in both classes, okay? Let's see if we break a record. All right, so now you understand. Oh my God, look at that. That is Schatzi. Schatzi is my cat, our cat, and we got him in 2006 from the Berkeley Pound, and his name is Schatzi. He was a feral cat actually, but he is a very good cat, brings all kinds of creatures into the house, and I'm not showing you the cat, my cat, because he's a beautiful name. No, it's a red cat, okay? Red cat. Red cat. Another mnemonic. Red cat. Reduction is cathode. Okay, reduction is cathode, the red cat. That means the cathode is always written on the right side. Okay, where the reduction happens, the copper 2 plus 2 electron is the reduction. You always write it on the right side. Red cat. Okay? So, that's Schatzi, all right? So now the potential, and we see if the potential is positive, delta G is negative. Okay, and we had a positive potential of 1.1 volt, and with this, N is the number of moles of electrons transferred, F is the Faraday constant in moles per electron, Coulomb per moles electron, E is in volts, okay, and if this is positive here, then the reaction goes. If it is negative, the reaction doesn't go spontaneously, okay? So this is what you need to remember. So, but how do I know if the reaction goes to this side or to the other side? How do I know that? So we have what we call the standard reduction potential. There's a table that you can find in your book. It used to be called the Latimer potentials, and Latimer is the guy who the hall is named after. He was a very famous professor, and he was the first one who came up with this and measured those potentials. And he said, actually, they were at the time oxidation potential, but forget it. You write everything as a reduction reaction. You write, for example, you write copper plus 2 electrons gives copper, metal. You write zinc plus 2 electrons gives zinc, metal. And then you have a standard system where you measure all these individual half cells. Each of the cell is called a half cell, and you measure the one half cell against a standard hydrogen electrode. A standard hydrogen electrode is an electrode that has, it's a piece of platinum that is flushed with hydrogen at 1 atmosphere, H2 at 1 atmosphere, and that electrode sits in a 1 molar acidic solution, okay? So that means that would be a standard electrode. What can happen? It can so if this would be the reduction, so if the reduction happens, it's a strong oxidizer. This is a positive potential here. The more positive the potential is, the stronger the oxidizer. That means it doesn't want to be the oxidizer, oxidizes something, it oxidizes the other pair, the other half cell, and it itself picks up these electrons. It wants to be in the reduced form, okay? It always goes into this direction. Anything below in the table, it can be oxidized by the one above. So now let's see, that didn't make any sense to you, didn't it? Of course it didn't, because you don't know what we are doing yet. So let's measure the potential against our standard hydrogen electrode. And this is automatically set to 0. We set this to 0. Standard hydrogen electrode potential is 0. Okay? And we measure then everything against it. And if we have a positive value, that's a strong oxidizer. And if it's more positive, it's a stronger oxidizer. And if it's even more positive, it's an even stronger oxidizer. And if it's negative, then it's a reducer. But we write it in this way, but then this reaction will go into this direction, so if it's negative. Now let's do that. Let's measure some potentials here. Okay. So the standard hydrogen electrode, maybe I should show, I need the whole picture, please. A little bit, now lower, 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 lower. No, opposite direction. Lower, lower, well, if you want higher, fine, higher, higher, higher. Okay, now closer, 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 closer. Take your time, take your time. Closer, closer. And now go a little lower, yeah, exactly, stop. No. Down a little bit, down, down, tiny little bit down, a little bit more. No, down. This is up. So for you it's reverse. So I want this picture down here. This here, I want to sit here. Okay, further, further, a little bit more, a little bit more. Excellent. Thank you very much. Okay. So what you see here, you see this piece of metal here? And it's on a wire here. See that wire? It's in a tube here. That's platinum metal, and it's a platinum wire. And that platinum wire is actually treated that it's platinum black, that makes a large surface. Platinum black is also platinum, but with a very large surface, so it doesn't reflect the light that well. And so this is this part of the tube. And then there's a second part. There's a compartment around here, which goes completely around that inner tube. And there's a gas line. And that gas line is connected with that container, with that gas tank down there. And we're putting hydrogen in there. Now let's bubble the hydrogen. And this is now 1 atmosphere of hydrogen, okay, in 1 molar sulfuric acid solution. And now we put copper sulfate and copper in copper sulfate, and we want to measure that potential against the hydrogen standard electrode. Let's see what we measure. So why doesn't it work? Wait, why doesn't it work? Salt bridge. Let's put the salt bridge in. Okay, 0.31. That's pretty good for such a fly-by-night experiment here. I'm sorry, Karen. But wonderful. 0.32 volts. And if we do a super precision experiment, it will be 0.34 volts. Okay? It's positive. Positive means that, the copper goes into the copper ions are reduced to copper plus. So if they are positive, this is the prevalent side here, okay? Now, where do these electrons come from? Hydrogen gas goes into solution and forms H plus ions and furnishes these 2 electrodes. There are 2 electrons, okay? And these are picked up, and the copper will plate out. So that means this is going to be reduced, the oxidizer is going to be reduced, and this is the reducer, it will be oxidized. Okay? Now, let's see what happens if we 0.33, look at that. Wow, that's superb. I hardly ever had it that good. Okay, good. Now let's take this out and let's do the other half cell and let's see what the potential will read then. You probably can already tell what the potential should be because it's written down here. So we have zinc, metal in zinc sulfate solution, 1 molar zinc sulfate solution, against a normal hydrogen or standard hydrogen electrode. And there we go, minus 0.73 volts, minus 0.73 volts. And if we do a high precision experiment, it's minus 0.76 volt. So this is minus. It's a lousy oxidizer. It's an excellent reducer. So if it's a reducer, it gets oxidized itself. So everything that's above, if you have 2, for example, the more positive goes this way, the more negative goes this way. All right? It doesn't have to be necessarily 0. If you have anything above here, the more positive goes this way, the more negative goes this way. So now what happens here? So this zinc goes into the solution and has these electrons, and these electrons are picked up by the hydrogen ions in solution, and it makes hydrogen gas. So this gets oxidized, and this gets reduced, okay, from oxidation state +1 to 0, and this from 0 to +2. I think this is a beautiful experiment, 0.73. All these experiments are beautiful. We should give a big hand to Karen. Thank you very much, Karen. And also to the camera. Excellent camera. Thank you. All right. So let's see if you understand. So this is how you write this. The copper minus the zinc. So it's the right minus the left, or the red cat with the cathode minus the anode, okay? You can right minus left, you can, for example, do, okay? But you have to have the reduction always on the right side. The red cat is on the right side, okay? So this is how you write. This is the electron that I just explained to you. This is platinum wire, and the hydrogen bubbles around here, and this is in 1 molar. What's this the solution we're using, Karen? HNO3? HSO4 she uses, okay? Sulfuric acid, 1 molar. So that was, the potential is, if it goes this way or this way, it's always 0. And we write this with the first half cell would be platinum, H2 gas, and then separated with H plus in solution. Bridge here, copper 2 plus, gets copper reduced, and this is plus 0.34 volts. The other one goes in the opposite direction. Platinum, H2 plus, AH2, H plus, and the zinc, what happens with the zinc? The zinc goes in solution from the zinc metal, so it goes this way, and this is minus 0.76. That's how you write a complete galvanic cell, all right? But be careful, if you don't have platinum, you always write the reduction on the right side, okay? So in this case, the reduction would be this here. We would have to transfer this. We would write the zinc here and the hydrogen here, but I wanted to show you the difference, okay? This is positive and this is negative this way. So, now let's see if you understand. This is our copper. And copper, does it want to be in this form or in this form? It's a positive potential. And we place copper in 1 molar sulfuric acid. What will happen? The copper will go in solution, hydrogen will be formed, or nothing happens. Why don't you think about this and give me your answer, please? What state does want the copper be in? Would it be it likes to be metal, or it likes to be copper ions? Did Henry Doe show up? Everybody knows that Henry didn't come to lecture. Is anybody his friend? Can you give him his book? You see him today in the lab? Thursdays. So maybe you get. I'll try again on Wednesday. If anybody sees Henry, I'm going to write him an email. Let's see. It's going to be like this, huh? No, that's pretty good. It's not right, but it's pretty good. So what did I say? I said, no, we don't want to do that. That's obviously this one here. So oxidizers like to be in its reduced form, isn't that right? And reducers like to be in the oxidized form. So why don't you discuss this with each other and try to give me a revised answer, at least some of you? Come on, have a discussion. Will this dissolve or won't it dissolve? What happened? Or did I never start it? I did. Yeah, it's a majority. Okay. Why don't we do that experiment? Let's do that experiment, please. So we have 1 molar sulfuric acid and copper. See, that's copper metal there. Can you shake it a little bit? Okay, now we said nothing, the majority said nothing. Let's have a look at this. Of course, nothing. So Karen puts in the sulfuric acid. You see any gas or anything? Nothing, nothing. Nada, niet. Okay, nichts. Yeah. What's in Japanese? What's nothing in Japanese? No Japanese here? Okay. Nothing I can. In Chinese? Mo ye? Nothing? Mo ye. Okay. All right. So, obviously nothing, of course nothing happens, because the copper wants to be in the metallic form. It doesn't want to be in as copper 2+. It wants to be in this form, has a positive reduction potential, so it wants to be in that form. The more positive the potential is, the more it wants to be in this form here, okay? So this is 0.34 volts. All right, so let's have a look at that here. So this is, that measures, I told you, that measures 0.34 volts here. And with this, the answer was the hydrogen is already there and the copper is already there, so nothing happens. Absolutely nothing happens. And with this, nothing. Okay? So now let me ask you a question. If you have zinc and sulfuric acid, this goes, zinc is a negative reduction potential, minus 0.76 volt. Does it go in this direction or in that direction? Why don't you give me your answer and say, what happens when zinc is placed in sulfuric acid? You can have zinc 2+ and hydrogen 2+, hydrogen gas evolving, or nothing can happen. Or you can both of those, but you don't have two clickers. I haven't started it. Wow. That's not good. Okay. So give me your answer, please. So on Thursday, there's a review session by Greg Dallinger. No, he's not here. Usually he sits there. Thursday, 5 o'clock here. And he's trying to get another review session next week, but not on Thursday, either on Tuesday or Wednesday, if he can get the room. And my office hours are Wednesdays from 4 to 5 and Fridays from 3 to 4. The more the merrier. 446 Latimer Hall. So what happened? How about B? The electrode's got to come from somewhere. Okay. Let's see what the answer is. Yes! You got everything, because if you understand that, you understood the whole lecture. The coin dropped. Excellent, excellent. Very good. It's B, actually. It's B. But it's also A. So let's have a look at that. Let's have a look at this, please. Zinc metal, See, what's that bubbling here? What's that? Hydrogen gas, okay? So the hydrogen gas, so the hydrogen ions get reduced by the electron, by 2 electrons to form hydrogen gas. Where does these 2 electrons come from? The zinc metal goes in solution, makes zinc 2 plus these electrons, they get picked up by this baby here and makes H2. So the zinc 2 plus is right, and the H2 is right. And with this, we have the solution here. So the zinc goes in solution, and the hydrogen will be formed from this, as I just explained it to you. So A1 and 2, or A and B, was right. Okay? Everybody nearly got it. Excellent. And with this, I think we're not going to do anything anymore. We want to be there. With this, I wish you a happy Monday, and I see you on Wednesday.